Welcome student in our today's online section of subject Mechatronics. Today we are going to start our chapter number 4. Okay, so here we are. Name of this chapter is Time and Frequency Domain Analysis. So in this chapter we are going to see the analysis of system on account of its time and frequency. Then there are two types, time domain analysis, and next one is the frequency domain analysis. So first we are going to start with this time domain analysis. So here, on the basis of the response, which is the output of the system, we are going to study it on the basis of time. So that's why we called it as a time domain analysis. So here, after deriving mathematical mode of system performance analysis can be done by various methods such as time domain and frequency domain analysis. The basic may be set up by specifying parameter test input signal and by comparing the response of various systems to these signals. So here we are going to study the signal on the basis of time domain and frequency domain. So naturally, following standard input signals are used to identify system performances. First one is the step function, then second one is the pamp function, then impulse function, and fourth one is the parabolic function, and fifth one is the sinusoidal. You all are familiar with the sinusoidal and this input panels here. So time response analysis is a plot that describes the behavior of a system and contains much information about it with respect to time response specification and contains more information about it with respect to time response specification as overshooting, setting time, peak time, rise time, and steady state error. So on this specification of time we are going to do the time response analysis. So in this we will get the setting time, peak time, rise time, and overshooting time. So classification of time response, it can be classified into two. The signal classified into two. First one is the transient response and second one is the steady state response. So here you can see on x-axis we plot the time and on y-axis we are having the magnitude of response or magnitude of output of system. So initially, where the response is continuously goes on changing, we called it as a transient response, and when this response undergo a steady state, we called it as a steady state response. In this steady state response, the response does not vary more than the 2%, and in this transient response, the response is varying very rapidly. That's why we called it as a transient, means changing response. So transient response of a control system. As the name suggests, transient response of a control system means changing with time. So this occurs mainly after two conditions, and these two conditions are written as follows. First condition is just after switching on the system, that means at the time of application of an output signal to the system. So whenever you start the system, there is a change in its response. So this is the type 1. And second condition is that just after the abnormal conditions may include sudden change in the load, short circuiting, etc. So whenever there is abnormal change, there is the change in system response. So this is the transient response. And then steady state response of control system. Steady state occurs after the system becomes settled and at the steady state system start working normally. Steady state response of control system is a function of input signal, and it is also called as a forced response. So here you can see, when the system gets stable, we called it as a steady state response, and when the response is fluctuating or changing continuously, we called it as a transient response. The standard input test signal. So these are the various four type of steps signals which we are going to study. So this is the first type of step signal. The step signal defines the sudden change in properties of actual signal. It is being used to see the transient response of system, as it gives you the idea about how the system replies to interruption and somehow the system stability. So here, whenever the step response occur, it is mu of t is equals to under in bracket a when t is greater than 0, time is more than 0, and it is 0 when time is less than 0. So when a is equals to 1, the step is called as a unit step signal. Here it is, you can see it is the unit step signal representation. Example of unit step signal is that if the input in an angular position of a mechanical shaft, a step input represents a sudden rotation of a shaft, then switching on a constant voltage in an electrical circuit, sudden opening or closing a valve, all these are the step signals. Then here we are having the ramp signal. The ramp signal tells you the constant velocity attribution of actual input signal. Here you can see the response of system is continuously goes on increasing. Constant velocity attribution is there. It is being used to determine the behavior of system with velocity factor. So here r of t is equals to in bracket 0 when time is less than 0, and the response is a of a into t when time is more than 0. When a of t is equals to 1, the ramp signal is called as a unit ramp signal. Then we are having third type, it is a parabolic signal. A parabolic signal gives the constant acceleration distinction of actual input signal. It gives the idea about how the system will respond along the acceleration. So here p of t is equals to in bracket 0 when time is less than 0, and when time is greater than or equals to 0, then it is at square upon 2. When a is equals to 1, the parabolic signal is called as the unit parabolic signal. Here you can see how this parabolic signal can be seen. Then impulse signal. Impulse response in control system imitates sudden shock quality of actual input signal. Impulse is the output of system when given by small input. Impulse response emphasizes on change in the system in reaction to some external change. It is the reply of a system to the direct data input. So here gamma of t is equals to 0 when t is not equals to 0, and it is a when t is equals to 0. So it is the impulse signal you can see here on the screen. Impulse signals are obtained when there is a sudden shock to the system is got. Now this is the important concept asked many times in the examination, that transient response specification. So here we are. The transient response of a practical control system often exhibits a damp oscillation before reaching a steady. Here you can see it is a damp oscillation response. In specification, the transient response characteristics of a control system to the unit step input, it is common to the name of the follows. Here you can see it is the time plotted on x-axis, and there is the magnitude of response plotted on y-axis or output. And on this you will see this T of R, T of P, T of S. So all these are the various parameters on which we are going to study the time analysis of system. So here delay time denotes by T of D, which is T of D, it is the delay time. Then rise time, it is the T of R, so this is the rise time. Then T of P, it is the peak time. You can see T of P from this to this, it is the peak point. We will study each the parameter in brief as we proceed on the next slide. So here we are. So what is this delay time? So the delay time, it is represented by T of D, the time required by a response to reach the 50% of the final value of the first time. It is this time is known as the delay time. Here you can see T of D. This is the complete response, and 50% of this will be that point, and the time required to reach this 50% of this response, we called it as a delay time, which is denotes by T of D. Then rise time. The rise time TR is the time requires for the response to rise from 10 to 90% of its final value. So here you can see rise time. So it is the time required by the system to reach from 10% to 90% here. 10% to 90% of its final response. So this is the final response, and the time required from 10% to 90% of this final response, it is considered as the rise time. Okay, so rise time can be calculated as C of t is equals to 1 minus e raised to power of omega t into sine of omega under root of 1 minus zeta square t plus tan square tan inverse of 1 minus zeta square upon zeta upon under root of 1 minus zeta square. So these are the formulas which we are going to require to use while doing the calculation. I will teach you these calculations and how we are going to study the time analysis as the unit proceed further. Okay, so this is the peak time. This time is represented by Tp, the time required by a response to reach the peak value for the first time. This time is known as peak time. Here you can see this is the peak, and the time required for this response to reach from 0 to maximum value of this response, we call it as a peak time, T of P. Peak time is clearly shown in the time response specification curve. I just show you. So these are the formulas for this peak time. T of P is equals to pi upon omega into in bracket 1 minus zeta square. So I will teach you this how we are going to use this formula when we are going to take the numericals. Then setting time. This time is represented by T of S. The time required by a response to reach and within the specific range of about 2% to 5% of its final value of the first time. This is known as the setting time. Here you can see T of S, it is the setting time. This is the time required by the signal or system to reach from starting to the point where only 2 to 5% variation is there. So at the end of this transient response, we can say it is the setting time. Setting time means it's the time taken by the system to reach to the response where the response varies only 2 to 5%. This time required by a response to reach and within the specification range of about which is 2% to 5% of its final value for the first time. This time is called as the setting time. Setting time is clearly shown in the time response specific curve. I have already showed you. T of S can be calculated as 4 upon omega into zeta. Then maximum overshoot. It is expressed in general in percentage of the steady state, and it is defined as the maximum positive deviation of response from its desired value. Here desired value is the steady state value. So it is maximum deviation. The maximum percent overlook M is the maximum peak value of response curve. The curve C of t versus t means it is at which the system got stable. It is C of infinity, and it is the C of peak value. So C of Tp minus C of infinity upon C of infinity into 100, we will get the maximum percent overshoot. It is the maximum value of response at peak, and it is the maximum value at steady state. And in this way we will get the value of maximum overshoot, the percentage account that the signal overshoot of the steady state. Okay, so here we are having we need to use some formulas while solving this numerical of this time analysis. So okay, first whenever the system it is in the second order, which is mx plus m into d2x by dt square plus c of dx by dt plus k of x is equals to f of t, where m, c, k are the constant and which are mentioned in the numerical. So at that time we need to find the roots, then damping ratio, undamped natural frequency, then damped natural frequency, time constant, stability. So these are the formulas. I will show you this formula where we are going to take the numerical. So now you can read here, this roots is equals to S12, as it is the second order response, so two roots are available there, minus c plus minus under root of c square minus 4 mk. This is the formula, similar to minus b plus minus under root of b square minus 4ac upon 2a. I already teach you this. Then damping ratio, zeta is equals to c upon 2 under root of mk. Then undamped natural frequency, which is equals to under root of k upon m. Then damped natural frequency is equals to wn omega n into 1 minus zeta square. So this is the maximum percent overshoot. It can be calculated as mp into 100 into e raised to the power of pi upon zeta into upon under root of 1 minus zeta square. This is the formula for the peak time, the time needed for the response to reach the first peak of the overshoot, which is can be written in mathematical format as Tp is equals to pi upon Wn into under root of 1 minus zeta square. Similarly, we are having this formula for the delay time. T of d is equals to 1 minus 1 plus 0.7 zeta upon omega n. The formula for setting time, it is T of S is equals to 4 upon zeta into W n. The rise time formula, T of R is equals to pi into B pi minus beta upon omega d. Okay, from the next section I will we will take some numericals of this time frequency analysis, and from the next section we will study about the frequency domain analysis. So here we are stopping today. See you in the next section.